Thanks for the invitation. This is really very interesting, particularly for somebody like myself, who's some sort of an amateur AMO kind of person. And so that's now there's a number of peculiarities here. The other thing is we're switching gear. Until now, frequency was very, very important. At this point, frequency is irrelevant, at least the frequency of the light used for this thing. And then finally, I can't resist saying that people have all sorts of cute acronyms, and we don't, but we have a little cute sort of little animation there. All right, so the idea is that I'm going to be describing the beginning of a new technique, hopefully to do gravity measurements at short distance, and this is using levitated microspheres. And I'm going to be essentially giving the motivation in terms of measuring gravity at short distance, just for a few slides, and then actually go through a number of non-gravity results and new technical developments that are used to essentially to lay the foundations that then are going to be hopefully used to actually measure, do the gravity measurement. Sorry, I'm trying to find. Okay, good. Better laser. And with the idea of actually doing a first gravity measurement in the next, hopefully, few months, in a range between, that's a typo, actually, should have said 10 to 50 microns. I think 1 micron is kind of for later, but in the range of 10 to 50 microns. All right, so first of all, in terms of sort of motivation, clearly, gravity has a number of distinctions. The first one is that of the 4 fundamental interactions, is the only one that DOE doesn't fund or doesn't fund research for. I have no idea why, but DOE funds, if you want to study electromagnetic interactions, strong or weak interactions, they're all fine with that. Gravity is just out of their domain. It's also the most evident of interactions, the weakest. And, it's really the least known or the least well measured in general. And this table pretty much summarizes the difference between interactions. And I guess the only other thing to add is that there's no such thing as anti-gravity, which explains why, celestial bodies, gravity only adds up. And so if you have planets, they all orbit dominated by gravity, and electromagnetic interactions are irrelevant from the point of view of, say, the moon going around the Earth. But once you get to short distance, on the other hand, things are different. And Eric has been telling me since in the last 5 years that the trouble is with electromagnetic interactions, and I guess he's right. But hopefully we'll overcome those things. Anyway, so that's actually the landscape in very, very crude terms or general terms. I think in general one can take the point of view of saying that gravity is so important, understanding better gravity is so important that I don't care what the theorist tells me. That's, if I can improve such a measurement, is worth doing. In addition, there are reasons to suspect that there might be deviations on the inverse square law at very short distance. And of course, whether it's really 10 microns or other scale, I think theorists always tell you that you're about, that the next order of magnitude is where the effect is going to be, which you may or may not really believe. But it is true that there is a number of theories that would actually have the inverse square law violated at short distance. Okay, and I think everybody here knows enough about all these things that I don't need to I can actually skip my next slide. That is in the way of motivating this. The experimental challenge, on the other hand, I think is can be summarized here. First of all, the force to be measured is really small, because you see when essentially you work at constant density, both attractors and attracted particle objects have density of like 10 or something of that sort, 10 grams per cubic centimeter. You cannot use neutron matter to actually build your attractors, unfortunately. And so at that point, of course, when you want to go closer, that means also the volume essentially of your object becomes smaller and smaller. And so if you're measuring a force, that force scales sort of this way, that is become smaller with the fourth power of the linear dimensions of the measurement. In general, maybe oftentimes you measure really more like an acceleration, use the equivalence principle to do the measurement, and you really measure an acceleration. But even then, you are still, the effect still goes down linearly with the size of the, with the scale of the measurement. So clearly, when you go to very short distance, the forces to be measured are very small. And as you go, as I already mentioned, below, let's say, 100 microns, even for neutral matter, E&M electromagnetic interactions are a dangerous background for those measurements. I always like to add a little sort of note here, is that in principle, if we were smarter, we would use neutrons to do those measurements. Those are more neutral than neutral atoms or ordinary matter. But for the same reasons, actually, Savas Dimopoulos likes to say that neutrons don't have handles, which is actually both a feature but the curse of this, because it's very hard to manipulate neutrons. And so there are some measurements at very short distance with neutrons, but they're not very sensitive, and so they're only applied to very, very short distance where you can't do anything else. But I think in general, it would be interesting if somebody would have an idea of how to use neutrons for measurements, at like, let's say 1 to 10 micron scale. Of course, you parameterize what you see by adding a Yukawa term with some sort of strength of this new interaction or the deviation of the interaction, and the scale lambda at which this happens. And so generally, that parameterization generates a plot like this, where you have the strength alpha here and the scale here. And you can see the yellow part is kind of excluded by previous experiments, and some examples of theories are shown here with various sort of lines. Let's see, notable, of course, there is at larger scale, that is between a millimeter and, I don't know, 20, 30 microns, there is the torsion balance measurement done by Eric's group. And then there is actually still a little sliver. This is Aaron Kapitulnik's and the microcantilever measurements. And then there are those measurements here are done with techniques that are really more common in condensed matter physics and so on. And then things sort of shoots up very fast here. Neutrons are down in this region at very, very short distance and way up there. Okay, and by the way, this is 1, so the strength of gravity is here, right? So actually, I think the Etvosh measurement at 40 microns is the is the shortest distance at which the sensitivity is 1 for gravity. Okay, so the idea is to actually move away from this from the standard technique and use something which is not a mechanical spring to do the force measurement. And it's kind of timely that this year's Nobel Prize went to Art Ashkin, who essentially invented the technique of optical tweezers in general. And in fact, through my talk, I'll be mentioning Ashkin a few times, because he actually had little notes in some of these papers, and he discovered or hypothesized each of the effects we see one by one. So it's kind of depressing. But anyway, at least one can say that I couldn't take good photographs in those days, because this is kind of not sure. Maybe this is the microsphere or something. But but the idea is that you essentially have, first of all, you do this in vacuum, and you have a laser beam that is propagating upwards, and you use the radiation pressure to counter Earth gravity, which in this case is just a nuisance. And then you use the fact that the laser beam is focused to actually have a force, the restoring force, which is axial, and keeps the microsphere essentially trapped. And so this is actually this trap is in general stable on all 3 degrees of freedom. If there's no air at all, in other words, if there's no damping term from the air, it's easy to actually heat up the microsphere, and so you need feedback to actually keep this situation really stable. And I'll talk about this in a minute. But the idea is the following now, that you have at certain distance, you have an attractor, which now looks like, let's say, my hand with various fingers sticking out that way, or some sort of comb. And then you move the attractor in front of the microsphere. And of course, the comb is not really, doesn't have real individual teeth, but you have a structure which alternates different densities, and then it's got a shield and all sorts of things that I'll discuss more in a minute. There's a number of advantages here, at least in principle, and that is that, and the microsphere, by the way, is few micron diameter, maybe 5 to 10 micron diameter. There's a number of advantages. Maybe the most important one is that once you are in good vacuum, the microsphere is really isolated from the external world. And in fact, you cool this thing down by using, again, feedback cooling to millikelvin temperature, while everything else is a room temperature around it. And it's very nicely decoupled, as we'll see in a few cases, from the outside world. And then you can use all the tricks of AEMO or quantum optics, for instance, to change potentials very quickly, or to manipulate this thing in various ways. So at least in principle, there's a number of nice features. But of course, this is a brand new technique, and torsion balances have been around for a long time. So, it takes a while to actually get up to speed and presumably and hopefully go beyond state of the art. The first thing you have to do, the first thing you have to do, it takes a year, the first time you try, and is how to actually drop those micron-size microspheres and grab them in the trap and so on. But that's kind of very technical at this point. It's just it's not interesting anymore. But the next thing you have to do is that, of course, those microspheres are electrically charged, and so first of all, you have to discharge them. And actually, this is the first of Ashkin's plots. We do much better than this. The signal-to-noise ratio is much better, but you can see very, very clearly the single electron steps, and Dave Moore tomorrow will show this directly. But in practice, this is totally under control. You can neutralize the microsphere and measure the charge with essentially, fantastic resolution. So on the other hand, what we don't understand as well is how to affect the permanent electric dipole moment or multiple moments of the microspheres, and that's of course problematic. And we'll probably get, even with the current electric dipole moments, we'll be able to do measurements. The hope is that maybe we'll manage to actually neutralize those too, same as we've learned how to neutralize the overall charge, but we're not there yet. Okay, the next thing is, as you can see here, is really convenient to be able to access the microsphere in the horizontal plane that contains the microsphere. And generally those traps are stabilized in order to stabilize the vertical degree of freedom, there is an auxiliary laser beam that essentially propagates where this yellow thing is in that plane. And so we've modified the system, or our system at this point runs with a single laser beam, which is, by the way, 1064 nanometers. But again, the frequency is not really, the wavelength is not important for us. That's just a convenient wavelength to use. But the trap is user interferometry on all 3 degrees of freedom, and in particular, it measures the height of the microsphere not by a shadow produced by an horizontal laser, but by looking at the back reflection from the microsphere, and then that is interfered back with a reference wavefront that comes from the same laser. So that essentially you count fringes and you measure the height of the microsphere by counting fringes, meaning this is also absolute calibration, there is an absolute calibration in units of 1064 nanometers. So that works really well, but it essentially does everything with a single beam. That means that you have very good accessibility around the horizontal plane to do other things. There is also interferometry done in the other 2 degrees of freedom. In other words, what you see on a position sensitive photodetector is not just the the light coming from the trap, but the interference of that light with another reference beam and or wavefront. And that means that if you have, that suppresses to some extent light that is scattered off other objects inside the trap, and that actually undergoes a different path length to the photodetector. So this improved things some, but there's still issues having to do with scattered light, at least in the trap that is shown here, that hopefully that are to some extent fixed by a more recent trap that we built. The other thing is that the quadrant photodetector, essentially, if you think about it, there's only 4 or 8 channels. There is essentially 4 amplitudes and 4 phases. And you are measuring the position of the microsphere by using this information. But in reality, if you had more pixels, this would be more, there would be more information you can use. You can imagine, for instance, if you start clipping the beam of the trap, you start from a beam that is kind of round, from a shadow that is kind of round, and the shadow becomes like a D-shaped thing. And now you can mistake that as being moved, as the center of light of the thing being moved, but in reality it's just that you're clipping. And if you have more pixels, you can actually see that. So we actually have made 10 by 10 photodiode pixel, or 10 by 10 pixel photodiode arrays, and we're building electronics to read them out. The idea being that you actually get quite a bit, you get a rudimentary image with the high bandwidth that we actually need. And so, but that's something for the future. So now, using a trap of this type, we get a noise that looks sort of like this. This is actually the full noise, if you want, the blue line, and those are this is noise, say, without microsphere. So this is like the jitter in the pointing of the laser, and these are other instrumental effects. This is the shot noise limit, and if you look in this region here, that is, like 20 to 50 hertz or something, which is where we plan to do measurements. You see that we're still a couple of orders of magnitude at least above shot noise limit, but for the measurement of gravity, that's not that's not the limiting factor yet. But there's plenty of room to actually improve this and at least reach the shot noise limit. Or the quantum limit, and so we are actually working in parallel to improving this thing. Having said this, the acceleration noise is essentially the best, at least at the time last year when this thing was published, that there is around. If you convert this thing into a force noise, it's not the best because our microspheres are quite large compared to some of the nanospheres that are used by others. Yes, sir. Yeah. Oh, sorry. Yeah. Okay. Yes. And then the other thing is the trapping lifetime, by the way, including charging lifetime, is infinite. That is, you put this thing in the trap, and weeks later, it's still sitting there and it's still neutral. So that's actually, from that point of view, this is a very well-behaved system.
What is F1 and F2? Just the other two directions?
These are the other two directions. Yes. You'll see more of this in a minute, actually. Okay, so I already anticipated this, but let me show you a little bit more how this thing works in practice. The trap looks like this. This is not the most recent trap, but it's close enough. There are electrodes which are made like truncated pyramids. You see the end of it here. And so that you can, first of all, you have shielding around. You have a nice equipotential situation around the microsphere. Through those holes, there is access for the beams, and electrostatic charges that are on the lenses that make the trap, at least that trap was done with lenses, are actually shielded out by those things. It turns out actually that without those cones, you can infer the charge on the lenses, and it's remarkably similar to the amount of charge that LIGO claims they have on their mirrors. So this all sort of, goes well together. Through one of the holes, you actually you insert the attractor that looks like this. This is actually, there's no pattern drawn here, but you can imagine here the fingers of different density, and so this can be retracted, by the way, or brought back in. You can get at least to 5 microns from a microsphere. You can see here the attractor and the microsphere, the separation. Those microspheres are 5 micron diameter, so this separation here is 5 microns also. And again, this is actually at this point quite stable. You can actually go even closer than that. Although when you get very close, you know, the force on the microspheres are, for the time being, not well understood. As you get closer, first of all, there is you perturb the mode of the trapping beam, and so you have both something in the shadow that changes, and also you are changing the position of the microsphere by essentially affecting the details of the beam. So that's something that we need to control carefully. And then there is the fact that there are electrostatic forces between the dipole moment of the electric dipole moment of the microsphere and patch potentials that are potentially on the surface of the attractor. And then finally, there are Casimir forces to worry about.
You don't need to say potentially, they're there.
Well, I say potentially because I haven't showed you the thing yet, but yes. Okay, and then there is Casimir forces, although those are actually expected to become dominant at shorter distances. For the time being, that's actually not the most important thing. This is actually can be used to essentially scan patch potentials, if you want, on the front of the attractor. And first of all, so you can imagine this is essentially like an atomic force microscope that is fully three-dimensional and has a very broad range, doesn't reach the same distance as an AFM, but has actually good sensitivity over, you're really measuring, mapping a vector field in all 3 dimensions. And so this is shown, this is actually the noise shown here. The little arrows are vectors. Again, there's 3 degrees of freedom, there's 3 coordinates, so this is always a little bit tricky to visualize, but this is now, those directions are Z and X, and then Y is in the board. There is the silicon beam that is gold-coated sticking out here, and at each point of relative position between this thing and the microsphere, you can see the forces measured on different planes coming out of the board. That's actually what those things mean. And that's actually the vertical scale, or actually the scale out of the board. And you can see the noise in the 3 degrees of freedom is actually, so it's of the order of attonewton, is few attonewton in X and Z for reasons we don't totally understand. It's a little bit larger in Y. Anyway, from the point of view of force sensitivity, this is good enough to do the kind of measurements we want to do. Typically, this has the same noise as cryogenic AFM, but you cannot get as close as AFM. But on the other hand, you're really fully three-dimensional. You're actually scanning a large volume. By the way, this goes only to 100 micron. The scan here is only 80 micron by 80 micron by 80 micron in the other direction. This is just accidental. The stage we had in vacuum at that time could only do that. Only had a throw of 80 microns. And actually now we have a stage that can do much larger scans, but you can do much more than this. So now, okay, so this is the noise. Now you can actually apply a real force, which you can do electrically by just putting a bias on the cantilever, and that's actually the force you're measuring. Those are, okay, so the black long arrow is 3 × 10⁻⁴ Newton, well, black and red. Black is the measured, and red is an FEA, is a finite element analysis simulation of the situation. You see, the thing, agrees sort of really well. And this is very linear over a couple of orders of magnitude, or at least an order of magnitude of force. Okay, those are large forces which are obtained by applying, 10 to a volt there. Incidentally, again, this is from one of Ashkin's papers, and he predicted that this is something one could do. Okay, so the next thing we need to do is to actually or would like to do, is to actually characterize the microsphere. Those microspheres are very small, they're very generic. Are they all the same? Are they very round? What's the mass and all that? And it turns out that generally, so actually this is one of the students in the group pretty much invented the way of doing the measurement, which I think is quite remarkable and new. So the idea is that the microsphere is actually held up by the radiation pressure from the laser. If you knew how to measure very carefully the radiation pressure, which requires making some integral over the Gaussian mode and all these kind of things, then you could measure the weight of the microsphere. But that's not easy. And it's very hard to calibrate in some sort of absolute way. However, what you can do is that you can put a charge on the microsphere, since we can control the charge very well, and then bias the two electrodes on top and bottom. And now, as you increase the bias there, the optical field has to go down. The feedback will turn down the laser intensity to actually maintain it at the right level, within a fraction of 1064 nanometers. So that's actually very very good quality vertical measurement. And so as you do that, the optical power goes down, but now you're only measuring the relative optical power. You don't need to know the absolute optical power. And so you can extrapolate this thing down to 0 optical power. And when you do that, now you can extrapolate to the applied electrostatic force. And so now you're actually measuring the weight of the microsphere that way. And you can see you can extrapolate many of those things down, and well, actually these are many measurements for the same for one particular microsphere, and you see that the extrapolation works really well and is very consistent with itself. You can repeat the same measurement. There's 3 types for each microsphere that is separated by this kind of vertical dash line. There are 3 ways of doing the measurement, and I always forget which one is which, but you can actually do this with positive or negative charge on the microsphere. And we do the measurement in good vacuum or in kind of mediocre vacuum to check that there's no difference, and there's no systematic effect between those 3 cases in general. As you go from one to the other, there are legitimate differences, which are just the fact that those are different microspheres with different masses. So this is actually a powerful way of doing this. But then actually you can also, at the end of this measurement, carefully insert the attractor in and block the laser beam, and the microsphere jumps on and sticks to the attractor. And this only requires the student with the magic touch. But when you do that, the last 3 microspheres are actually, on your attractor, and you can see they're sitting here, 1, 2, and 3. And so now you can extract this thing very carefully, put it in a SEM, and measure the diameter of those very microspheres that you have there. And so that's actually what has been done. And in fact, and you can also get a large sample of microspheres from the same manufacturer, same lot and everything, and measures them all. And so that's actually what's shown here. The histogram is the measurement of, I don't know, like a few hundred microspheres. And those are the 3 measurements done on the 3 microspheres that were actually captured after measuring their masses in the optical trap. So this all works very well. There are 2 Gaussian curves here because we are unsure when you use the SEM. It's sometimes a good idea maybe to metallize the microspheres so that you're sure you don't get funny effects of repulsion of electrons and so on. But you see that the difference between metal, coating them with aluminum, gold and palladium, or not coating them is actually quite small. So there is a systematic effect, but it's small compared to the other uncertainties. And so the 3 microspheres are a good they represent well the distribution of the entire population. And so the radius is, the density from the mass that was measured and the radius ends up being 1.5 gram per centimeter cube, which is substantially lower than the density of fused silica. And that means presumably those spheres have some non-trivial porosity. Those are grown with the Stober process from some sort of aqueous solution or something. And there's chemistry involved that I definitely don't understand, but They are supposed to have some sort of maybe OH groups stuck on them or this kind of things. Wow. Okay, and then don't worry about this Stover process. Then let's move on. So since we are not good enough to measure gravity in general yet, at least we can try to make a measurement in a condition where the macroscopic gravity measurement doesn't work very well, and that is the case of those chameleon fields where Eric's attractor itself is so massive that we actually shield this field. And so that is just a test. The idea is that the microsphere is so small that, and the attractors here are so small that you have less of those issues. But in some sense, this is just also a test of the fact that that there are electric dipole moments. And so you can see we put the sphere in this range of distances here with respect to a cantilever. And then you have, as you move, now in this case you move the cantilever in and out, that is you change the distance between the two of them. And as you do that, you see how a permanent dipole moment and an induced dipole moment would actually behave. And in fact, you can apply deliberately apply potential to the cantilever, and here there are several from 1 to 5 volts, and then fit to the permanent and induced moment. And you see that you measure a permanent dipole moment, which is of the order of 100 or between 100 and 200 electrons micron. And the induced moment is small. I mean, it's subdominant and consistent with 0 essentially. And then what you do is that you repeat the measurement without, with the grounded attractor, that is with nominally 0 voltage, and you see something you get with different microspheres, something which is, which is consistent with a very small voltage on it, as it could be, that there is essentially a contact potential of maybe 50 millivolts or something, and that's within this thing, within what you see, and you can use that to essentially extract a limit on those effects. By now, this has been totally superseded by atomic interferometry. Of course, the systematics are very different, and no one really knows what all this means, really. So it's probably still interesting to do the measurements. But all right, so let me go on and talk about rotations in the last minute and a half. Okay. So one thing that is interesting is to actually see whether we can rotate the microspheres. Since Ashkin's times, people have looked into the possibility of using essentially having circularly polarized light to exchange angular momentum in the microspheres with birefringent microspheres and spin them up that way. Dave's group has done maybe one of the most recent pieces of work on this, and that's well established. But the idea is that if those things have an electric dipole moment, then I can essentially rotate an electric field around the microspheres and pull them, and drag them along. And so that's what you see here. The interesting thing is that you excite this rotation with the electric field, but you measure it because those microspheres are slightly birefringent, and so if you have linearly polarized light here, you can read out the wrong polarization state on the output and essentially get that information. And so you can see it here at twice the rotation frequency. Indeed, you get a very big sharp peak, and so that's essentially the signal you expect. There's also some side bands here, and those are librations. So in other words, in the reference frame of the rotating electric field, the microsphere does this kind of thing, as you would expect. And in fact, that is supposed to scale with the square root of the electric field, or the peak electric field, and that's exactly what happens here. From this information, you can extract the ratio between the electric dipole moment and the moment of inertia. If you assume that you know the moment of inertia from the measurement of, you assume that the microsphere is homogeneous, you can extract the moment of inertia, and so you're measuring the electric dipole moment. And you get numbers, you'll see those numbers again later, that are very consistent with the numbers I gave you before. You can also, at this point, let the microsphere go and watch it spin down. And at least down to a certain RPM, if you want, it behaves exponentially with a time constant that is consistent with gas dumping, essentially, from the residual vacuum. Once you get to very small RPM, there is other torques, including the optical torque, given by the fact that I'm using polarized light in there. But at high rate, this works really well. Now, there's a better way of actually measuring the gas drag, and that is I can measure now the angular separation, or the angle between the electric field and the dipole moment of the microsphere, or one of the polarization axes. And as there's more drag, this angle becomes larger because I have to pull harder to actually make it come along. And so until I get to 90 degrees, once I get to 90 degrees, then I unlock the microsphere, because now and that's exactly what you see. So you see here, let's try with this one. You see here that the phase lag, this phi ec whatever, changes, decreases as I increase the pressure in the vacuum chamber. This is done with nitrogen. And at some point it unlocks. That means now the phase becomes random. It just jumps up and down. Okay, now that depends on the voltage or the amplitude of the electric field I'm using, which is what you're seeing here in those three. In fact, there's more measurements done in intermediate fields, which are the green dots here. And those three, and all those measurements, so the relationship between the unlocking pressure and the electric field, or the potential here, is actually exactly what is expected. That is this red line that fits very well the data. Okay, so now using some gas dynamics, you can also calculate this thing, and this sort of comes out very well. I mean, this line can be sort of predicted, and it actually is predicted a factor of 2 in pressure different from what we measure in the vacuum chamber, but that's totally reasonable because vacuum gauge is somewhere else respect to the microsphere, which is really important. The other thing is that, and by the way, the prediction comes, or the calculation is done in this paper here, which is a LISA paper, a recent LISA paper. So you can also change the gas species and you expect different behavior. And sure enough, that's what you see. So you see here now I'm using helium, argon, and sulfur hexafluoride, just for something very heavy. And you can see that again, the unlocking pressure is different at constant electric field for the 3 different gases. And also the spin down behaves like you expect. And in fact, you can put it all together, and we've done, people who know my other activity know that I have lots of xenon in my lab. And so we couldn't resist doing this thing for xenon and krypton, argon, nitrogen, and helium. And you can see that this behaves exactly like predicted by the gas dynamics with very, very small residuals. So essentially, we built the world's smallest rotating ball vacuum gauge, which is, nothing very impressive actually, except this vacuum gauge. First of all, you can measure. That means you can really measure the vacuum at the microsphere, which is important for other applications. Also, since the measurement is always done by measuring this phase shift, this is much better a measurement. The regular rotating ball vacuum gauge, you see the spin down. You have to wait for the thing to spin down, whereas here you're just measuring this phase shift, which is actually very convenient. This is more like a playful thing. You can, when the thing is spinning, you can now kick it in the orthogonal plane, and these things start precessing, and you can predict the precession frequency, which also linearly depends on the voltage at which the field is rotating this way. That is the torque. Essentially, you're applying the other way. And again, this fits very well. Now, this is the gyroscope equation, essentially. All right. So now, last few slides, really. And this is about gravity. And so the idea, remember, was to... okay, so now that I can spin those things, though, there is one important thing. Eric's evil patch potentials, or dipole moment, gets averaged as the thing goes around, and since it's neutral, on average should be neutral. In addition, at high frequency, I should see the microsphere moving because of the dipole moment interaction with the patch potentials. Whereas at lower frequency, where the gravity signal is, I should average this out. So I should be able to measure independently the signal and the background. We haven't done this yet, but that's the idea. Now, in addition, you can insert a shield, an electrostatic shield that doesn't move. That's sort of more like brute force. between the attractor and the microsphere. And so what I'm going to do in the next few slides is actually show you the first attractors we have. So this is actually this is the attractor we are using now, or we started using now. It's fabricated on a piece of silicon. So the darker thing is silicon, and then you trench the silicon, and you actually fill the trenches with gold. So now you get the contrast between silicon and gold. In the part that is kind of hanging, or in the overhang here, the thickness of the material is like 10 microns. You can see it here. And you can see in general, and then the pitch of this thing is 25 microns. And there is a small part of silicon that is sitting in, that is sort of in front, which in some attractors is actually smaller than this, and on top of which some more gold is deposited. This is done before depositing the last coating of gold, otherwise you can't see anything. And I told you about the shield. Actually, the shield at this point is fabricated, and you can see it here, but that's actually the schematic of it. So there is essentially, in a piece of silicon, there is a pocket in which the attractor moves, and there is the slot in which the laser beam goes. So this is actually not only is an electrostatic shield that doesn't move, but is also an optical shield. In other words, if you are clipping the beam, it's clipped by this thing that doesn't move, and the attractor doesn't actually clip the beam because the attractor is sitting in this pocket here. Right. So also Dave's group is actually making microfluidic attractors where there are little droplets of liquid with different density that are pumped into a little conduit, which is used for this. But the chair is standing up, so I better hurry up. This is actually the system now as it's ready to take data. This is actually a new trap that was not the one I showed before. This is the trap itself in vacuum with the output optics and the input optics on a nice granite table. And that's the conclusions, which I'm not going to read. Well, actually, no, I want to read one thing on the controlling systematics, providing redundant tools, and setting up experiments with true discovery potential is essential. So I really would like to see that that if you simulate a signal somehow, you don't cancel it out in canceling backgrounds or something, but you can actually see the signal. Like LIGO, I like the idea LIGO makes blind injections and actually can find them. And of course, if there was a discovery, we would need many different techniques and different groups to verify that. And I'll just leave you with my group shown here, and thank you for the attention. And sorry for running over time.
Oh, that's okay. That's a Californian notion of time.
Right.
So, but we have,
And Italian. Put together Californian.
But we have, actually we have a few minutes time for questions. So,
So very interesting. So when you are rotating, if you bring another sphere, static one here, you can probably transfer the spinning.
Like little gears, yeah, right. We never tried. We only have one beam, a single trap, so. Yeah, but could be that there's something interesting there.
Also for spinning, could you use, in addition to circular polarization, could you use an optical vortex? Have an optical vortex beam for the...
So, right, so that's something, in one of the values in the ONR grant, we have something about non-Gaussian modes of the trap and so on. Yeah, eventually we'll do that. We haven't gotten there yet.
more questions? Then if not, let's thank the speaker again. Thank you.